Welcome to this class. This session we are going to discuss about harmonic functions. Do an example of harmonic to prove that a function is harmonic. So any function that satisfies the Laplace equation is called harmonic. So theorem, if there's a function f of z given by u plus iv, that is to say u plus iv is analytic, then f of z so if f of z is given by u plus iv, then both u is depending on x and y, and v are harmonic. So quick proof for this. Proof of a theorem. The fact that f of z is analytic implies that that function must satisfy the Cauchy-Riemann equations. So f of z analytic implies that u and v satisfies the Cauchy-Riemann equations. So-called the CRE. That is partial u partial x equals to partial v partial y, and partial v partial x equals to minus partial u partial y. So let's call this first Cauchy-Riemann equation 1. Let's call this one 2. Now, in question 1, differentiate both sides of 1 partially with respect to x, i.e. partial x of partial u partial x equals to partial x partial v partial y, which result into partial squared u partial x squared equals to partial squared v partial x partial y. Then we call this one equation 3. Similarly, differentiate both sides of equation 1 or equation 2 now, partially with respect to y, i.e. partial y of partial v partial x equals to partial y minus partial u partial y. Actually, let's use the same equation 1. So both sides of equation 1, those two. Equation 1. So I have partial u partial x partial v partial y. So we have partial squared u partial y partial x equals to partial squared v partial y squared. Call this one equation 4. So so this are negative, so this same thing, and then differentiate both sides of equation 2 partially with respect to y. So I'll have partial y of partial v partial x partial y minus partial u partial y. And this is the second equation. So this will be partial squared v partial y partial x equals to minus partial squared u partial y squared. Call this one equation 5. Now, equation 5, when you add equation 5 to equation 2, or simply say equation, so partial squared u partial y squared equals partial squared, since partial squared So this one here, from equation 3, this is partial squared v partial x partial y. So partial squared v partial x partial y is equals to partial squared v partial y partial x. Then from 3 and 5, we need to have partial squared u partial x squared to be equals to minus partial squared u partial y squared. On rearranging, taking this one to the left hand side, we'll have partial squared u partial x squared plus partial squared u partial y squared equals to 0. So you see that u is harmonic because it's satisfying Laplace equation. Similarly, so next one, we differentiated 1 with respect to y. So let's also differentiate 2 with respect to, this was with respect to y. So now let's differentiate equation 2 with respect to x. Similarly, differentiate 2 with respect to x partially, i.e. the second equation is this one here. So vx. So we'll have partial x partial v partial x equals to partial x minus partial u partial y, which tells us that we'll have partial squared u partial squared v v partial x squared equals to minus partial squared u partial x partial y. So call this one, which 6 or 5 from our labeling? 6. Call this one equation 6. Now equation 6 and equation 5, partial squared v partial y partial x is the same as partial so partial squared v partial y partial x is the same as partial in this one here. So partial squared v partial x squared is given by minus partial squared u partial y partial x partial y. So when I take equation 6 and then equation 5 is partial squared, so equation 4, partial squared u partial y partial x equals to partial squared v partial squared y. Then equation 3 plus equation 4, equation 3 plus 6 gives me so question 6 is partial squared v partial x squared equals to, I can say, plus partial squared u partial x partial y equals to 0. And then equation 3 is given by partial squared u partial x squared. Okay, let's question 4. Partial squared v, let's say equation 4, not 3. Partial squared v partial y squared, and then this will be now minus partial squared u partial y partial x. Note that partial squared u partial x partial y is equivalent to partial squared u partial y partial x. So when we add these two equations, then just have partial squared v partial x squared plus partial squared v partial y squared, which is 0. For this sum of this positive negative is 0. So this is also proving that v is also a harmonic function. So such functions u and v, which are both which defines f of z, where f of z is analytic, are called harmonic conjugates. So such functions u and v, such that f of z equals to u plus iv is analytic, are called conjugate harmonic functions. So such functions are called conjugate harmonic. So the next session will be proving that some functions are harmonic, and then thereafter we'll see how we can get v when you're given u, or how we can get conjugate harmonic functions. So thank you.